Good morning, everybody. Today we are looking at section 3.5. So again, there's only 3 more sets of notes after this. So your next test will be next week. Looking at the calendar or the schedule that we have, we've got about 19 days of this class left, and we're showing about 12 days of school left. So we may be going a little bit over the May the 8th deadline. But that has been cleared through EKU. But we'll talk about that later today in our Zoom class. So, when the sigma is unknown, we don't know the population mean. We've done this before, when the population standard deviation is unknown, and we've done this before when we calculated the t statistics. We use the z values when we know the standard deviation of the population. We use a t statistic when we don't know the standard deviation of the population. And we are going to use the formula that you see here. This is what we base that off of, where t is equal to x bar minus mu over s, which is the sample standard deviation, divided by the square root of n, which is the sample size. And we use the n minus 1 to represent the degrees of freedom that we have to use on the table when we refer back to the t table. And so when we set this up for the means of hypothesis test, it still looks very similar. It's x bar minus mu sub naught, or mu sub 0, which is the assumed population mean that we're testing. And this talks about the t-test, the left-tailed test, the right-tailed test. There's not really any difference between these 3 tests as it relates to the t-test or the t statistic. Because we know the t statistic is a curve, approximately normal, and so the same principles apply. We have areas to the left, areas to the right, and areas in the middle, or left and right rather, that we want to use as our rejection regions, and then the other areas are where we have our non-rejection region. This will be a quick set of notes because we only have 2 examples, so this will go quickly. But right here, what I want to look at is here in the middle of the screen right now. We're just kind of doing a quick for instance. So consider a right-tailed test with n equals 15, so our sample size is 15. Alpha is 0.05, so there's our significance level, and a value of a test statistic of t equals 3.458. So to calculate the degrees of freedom, take the sample size minus 1. The t value in this case of 3.458 is larger than any value in the t table. The largest t value on the table is 2.977, which corresponds to sub 0.005. And this in fact implies that the area to the right of 3.458 is less than 0.005. So in other words, our p-value is going to be less than 0.005, and because that is less than our designated significance level of 0.05, we can reject H naught, our null hypothesis. So we're going to apply that real quick here to 2 kind of very brief examples on example 1. For part A, it asks us to compute estimate the p-value for a left-tailed test where n is equal to 12 and t is equal to negative 1.938. So because it's a left-tailed test, we have to realize that we're talking about the area to the left of 1.938. So we're talking about this rejection region right here. And we also have that our degrees of freedom is equal to the sample size, which is 12, minus 1, which is going to give us 11. So because the t-curve is symmetric about 0, we know also that if we alternatively look at positive 1.938, the area to the right of 1.938 is equivalent to the area to the left of negative 1.938. And that's important because the t-table has only positive values. So if we refer to the t-table and we are looking for the degrees of freedom is 11, so that's this row right here, and we're trying to find the value of 1.938, it lies between these two values right here. Now, the t-table is not very precise. We have to make approximations based off of what information we're given on the t-table. So we know then that the area under the curve that lies to the right of 1.938 is somewhere between 0.05 and 0.025. Go back to the notes. So with the area under the curve being somewhere between 0.025 and 0.05, we obtain that from the t-table. We can reject the null hypothesis at any significance level that is larger than 0.05 or less than 0.025. For significance levels between 0.025 and 0.05, the table is not detailed enough to help us decide whether or not we should reject or not reject the null hypothesis. For part B, we're talking about a two-tailed test where n is equal to 25 and our t statistic is negative 0.895. So this is a two-tailed test, so that means we're looking at what lies to the left of negative 0.895. We're including that area, and we're also including the area to the right of positive 0.0895. So anything that lies in those two rejection regions, we would reject the null hypothesis. Again, we have to compute our degrees of freedom, which is 25 minus 1 is equal to 24. And anything that falls within this region, we would reject based off of the t-table. When we look at the t-table, we can see that we're looking for 0.0895, and when we look at our values that we're provided with on the table with degrees of freedom of 24, so let's highlight that row right here. 0.0895 is smaller than any other t value. The smallest t value that we have is the 1.318, which corresponds to t sub 0.10. Excuse me. So let's go back to our notes. So the area under the curve that lies to the right of 0.895 is greater than 0.10, and the area to the left is greater than 0.10. So and since we're talking about a two-tailed test, we have to double that. So 0.10 times 2 is going to be 0.20. So that's the area where we would reject our null hypothesis. And we are talking about if P is greater than 0.20, then we would not be able to reject the null hypothesis. However, if P is less than 0.20, we would be able to reject the null hypothesis. And again, the table, when we're talking about anything larger than 0.20, we need more precision with this table, and we're going to discuss that later on, how to calculate this using Google Sheets and get a more precise t statistic. But for right now, we're just trying to understand that these areas still apply the same way that they did when we were doing z values. So here is the one mean t-test. The assumptions are still the same. We're going to assume that it's a simple random sample, that it is a normally distributed population, or we have a large sample. And then here we have that sigma is unknown, so we don't know the population standard deviation. Null hypothesis and alternative hypothesis, those still remain the same. We have not equal to, which is a two-tailed test, less than, which is left-tailed, greater than, which is right-tailed. What we have changed is the test statistic, which is now t instead of z, because we were dealing with an unknown population standard deviation. And then the critical value approach, we would look at plus or minus T sub alpha over 2, or negative T alpha, which is our left-tailed test, or T sub alpha, which is our right-tailed test. And then we would go through and we compute that, and we would compare the rejection region to our T statistic. If our T statistic falls in the rejection region, we obviously reject the null hypothesis. The p-value approach, we find the test statistic, compare it to the probability, compare that probability to our significance level. If it's less than the significance level, we reject the null hypothesis. Otherwise, we do not reject the null hypothesis. So our second example and our final example, this will be a quick video today, talks about acid rain from burning fossil fuels. And there was a study of some lakes in the Southern Alps. A lake is classified as being non-acidic if it has a pH of greater than 6. The table that we have here shows the pH levels for 15 lakes, and we wanted to determine at the 5% significance level, does the data provide sufficient evidence to conclude that on average, the high mountain lakes in the Southern Alps are non-acidic. So just like we've been doing for this entire unit, we have to first state our null hypothesis and our alternative hypothesis. So the null hypothesis is that our mu is equal to 6 and our H sub alpha mu is going to be greater than 6. And that's where if the null hypothesis is that the pH level is 6, the alternative hypothesis is that if it's greater than 6. Sorry for laughing, guys. This first video I tried to make while Carla's in the same room with me, and she keeps peeking around the corner and staring at me. So the alternative hypothesis is that the lakes are not acidic, so their pH levels are greater than 6. And so we can see from the alternative hypothesis, because we use the greater than symbol, that this is a right-tailed test. And from there we can go on with the remainder of the calculations. We're given our alpha, our significance level, is 0.05. And we have to compute the test statistic. The mean of our data set is 6.6. I already calculated that in advance. So now let's compute our test statistic, which is going to be T is equal to 6.6 minus 6, which is our test value for mu, divided by the sample standard deviation. Again, this was calculated in advance as well. We just take that sample set. You could type it into Google Sheets and create the sample standard deviation. But it ends up being 0.672 divided by the square root of the sample size, which is 15. And when we calculate that, we get approximately 3.458. So there's our test statistic that we are comparing for either the critical value approach or the p-value approach. Now with the critical value approach, this over here, we have our degrees of freedom are going to be the sample size minus 1. So we have 14 degrees of freedom. And we have n is equal to 15, alpha is 0.05. And so when we go to our T table, we are first looking for degrees of freedom being 14. And then we want to find T sub alpha 0.05. Those two columns or rows and intersect at 1.761. So we have a T sub 0.05 of 1.761. Better. T sub 0.05 is equal to 1.761. The T statistic for 3.458, remember we're talking about a right-tailed test, so if it falls to the right of our test statistic, or if our test statistic falls to the right of our significance level, we will reject the null hypothesis. So if we imagine the curve here, anything that falls to the right of 1.761 will be in the rejection region, and 3.458 does in fact fall within that region. So we will reject the null hypothesis based off of the critical value approach. And then we can do the same thing now with the p-value approach. And remember, the p-value, we're just looking at areas under the curve. So the p-value is the area under the curve that is to the right of 3.458. And we already found that to be 1.761 based off of the when we go and look at the t-table and we find the area that corresponds to 3.458. So let's erase this. And we're going to scan the degrees of freedom. Again, we're looking at 14 degrees of freedom. And we're looking at 3.458. So 3.458 is going to be somewhere off to the right here. It's going to be well beyond the t sub 0.005. So that 0.005 corresponds to the area associated with 2.977. And the table would obviously, the values that I've highlighted in yellow will obviously get larger as we move to the right. And then the t sub values would actually get smaller. So we will assume, for the purposes of this example, that the t value, or the area under the curve, is 0.005. And we know that 0.005 is less than 0.05, which is our significance level. So again, because it's less than, we would reject the null hypothesis. What that tells us is, at the 5% significance level, the data that we have doesn't provide, or it provides significant evidence to conclude that on average the high mountain lakes in the Southern Alps are non-acidic. And that is the end of that. There's your homework questions. If you all have questions as you go through this, remember, just send me a message on Remind, or you can ask me later on today when we have our Zoom class. I'll be talking to you guys soon.